Okay, what are we trying to do? We're trying to make a box, and we're going to put balls that fall into it, and we're going to generate exactly 30. Okay, and this time we're going to generate the walls by creating the vertices. So let's just take a look at this. At this point, my view, there's the walls. And now I'm going to add the balls, but we haven't generated any balls yet. Let's just look at the axes to make sure we understand where things are. There's my 0, 0 point. And I think I'm going from 0, 2 to 0, 2. Yes, 0, 2 to 0, 2. So I got 3 vertices on that thing. So I can say wall list. There they are. And I just did a wall create command. So they're named wall 1, wall 2, and wall 3. Okay. Just a second. Yeah, okay. Now, we've got this command called ball generate. What this is going to do, it's going to create a collection of balls from a that have a size distribution, not a size distribution, just radiuses that go from a minimum to a maximum, uniform distribution, but you can control the number. So this is going to generate in the region of 0202, which is where our box is, radiuses that are uniformly distributed between 0.1 and 0.5 and make 30 of them. So if we do that, it says 30 balls were generated in 95 tries, and there they all are. Okay, notice that they're not overlapping. Let's do this. Let's make this not quite so much outlined. There we go. Notice if I tried to do 300, it's not going to be able to succeed. It says 36 balls out of 300 were generated, because from that size distribution in that box, if we do not allow overlap, this is the difference. The ball distribute command is going to have them overlapping, and you're going to keep throwing in there until you get to a desired porosity. Here, we just want to have them not overlapping. So, it's only what it does is it arbitrarily throws a ball and it checks, are you overlapping someone else? If you are, it says no good, try again, and it throws another ball. And it keeps on doing that. It does it up to, I think it does it up to like 200,000 tries. And after that, it still keeps failing. It's going to come back and say, sorry, I couldn't do 20,000 tries. It tries. So if you know they're going to fit, you can tell it, oh, make it do 500,000 tries and maybe they'll fit. But in general, they're not going to fit very well. They're not going to pack very well. But this is giving us 30. Okay, let's add a few things here. I want to put the cycle count step up over here, and I want to show the title at the top of the plot. So I can say this little check guy, this is information. That's not the right way to do it. Legend customer title, is that what I want? No, that's not what I want. Tools options. See, I can't even remember how to do this. That's not it. Oh yeah, right there, job title. Click. Boom. And it's not showing it. Job title here. Okay, there we go. So I had to go to this checkbox thing, which is allowing me to set information about that particular plot or that particular view. So I can say job title. I can also give a title just to this plot window. So I could say here, this is my system. Boom. Now it's also going to show that. It's going to show the title of the whole model, and it's going to show just this particular view. You're going to do that. Okay, let's get rid of that. This is my system. So plot title, don't click it, apply, done. There we go. Okay, generate the balls, 30 of them, give them a density and a damping, turn on orientation tracking so we can see if they rotate, turn on gravity. We're going to monitor a couple histories we'll talk about later, and then we're going to just solve until it comes to static equilibrium. All right, so if we run this, here they all go. And it's not really very instructive. I want to look at the force chains as it continues to cycle. So I'm going to say contact cylinder, text value, force chain, scale by force directed. It's still not in full equilibrium. You can see they're still vibrating. The force chains are changing a little bit. I'm going to make them black for compression. This is showing actually that when you want to get it to full static equilibrium for something like a packing like this, it takes quite a bit, especially if it's not. Now, if this packing was squeezed tight, it would come to equilibrium much faster. So there we go. After 1 e to the -5 ratio, we get to this state here. Okay. Now, just to demonstrate, let's take this wall here and I want to move it. So I'm going to say wall attribute x velocity, and let's give it a decent value, 0.3 meters per second. And then which wall? Well, these walls have ID numbers. That didn't work. Wall attribute, what is it? Wall. Oh, it's not x velocity. The command is velocity dash x. There we go. I can say wall list attribute velocity. Wall 3 has an x velocity, as you see, right? So now, of course, I can just cycle, right? And then watch what happens. So it's just going to push these guys. Now I'm doing this. Now they're going to eventually push out of the box. I have gravity on. Okay. Now watch. They're getting more and more squeezed. Those guys just flew out, right? They're just going to keep going down until they hit the domain boundary. Now what's going to happen? Pretty soon they're going to just be getting stuck here. Now they got really high compression, right? Now the question becomes, what's PFC going to do? Now what happens if this occurs? New, let's do a ball, no fill, black. And let's do a wall here. Now, let's make the wall red. So we start getting overlap, right? As the wall and the ball gets squeezed more and more. And as you remember with those cardboard discs and they started overlapping, and then we went and we took my pocket knife and we said that's the contact location, and we can make a hole through the disc. It's in the middle of the overlap region. This would be the case, the overlap region for a ball and a wall. And so this keeps going and the contact location goes here. But now, let's say that's the center. That's the center. Well, if this guy, as long as this guy is on that side, everything makes sense still. But if this guy gets to this side, what are we going to do? So what we're going to do, if this guy gets to this side, the contact location is going to go over here. Okay. We have to do something if this thing, because everything starts to break down if that thing gets past the center. So what we're going to do is we're going to make it flip so that effectively it's on the other side. So what's going to happen then is this is going to get really big, and then when it gets to the other side, it's going to get pushed out. And so here's what you will see. Look out. There's getting really big overlaps, and now it's going to go through the wall. Okay, and we could just continue this, right? As we keep pushing, they're eventually going to go through the wall. Okay, because now when it goes to the other side, the force is acting the other way. So instead of holding it in, it's going to shoot it out. Okay, this is what PFC is going to do. If the contact, if that overlap gets past the center, it's going to end up being on the other side. Okay, typically, in almost all cases, when you're doing modeling, this is an indication that you've got something that's not making a lot of sense. You're starting to get really, really big overlaps. Typically, that might mean your stiffnesses of your systems are much too low. your stiffnesses of your contacts. And so you're getting unrealistic large overlaps. Okay. Okay. Now let's do it again. But this time when we generate the wall, instead of just creating with the vertices command, let's do with the generate command. So now we can actually give it a name and we can say generate it a whole box of 4 walls. So if we do that, so we gave it the name vessel. And so with that command, here's the walls. And I want to say shape, facet, text, color by name. And so it, because it's a box, it put that, the name we gave was vessel. So it's going to add on the word bottom, left, top, right, right? So now we do the same thing. We generate it, the cloud, we let it do this, right? I'll just stop now. Now I can say wall, attribute, velocity, X, 0.3, range, set, name. Name is what? I want to do the left one. So that's vessel left. Range, set, name, vessel. Let's see if I got this right. Yes. And so now if I cycle it, and of course now I got that top wall, so they're not going to be able to squeeze out, right? So forces are going to develop here as I start packing in this system, and they're going to get higher and higher and larger forces as this goes on, right? All right, we'll stop that thing. Let's go and get rid of the top one so that it's a 3-sided box. So I'm just going to delete the one called the wall called vessel top, right? And again, let's look at this thing. Forces build up. Going to take a relatively long time because there's these adjustments that keep happening, like that guy just rolled over, right? There's still little bits of adjustments that have to occur, which means that those adjustments, see this guy, he's actually moving to the right. So the entire system is not in static equilibrium. There, now he's done. Now we're in static equilibrium, right? What is the thing you see about the force chains? What is one thing you notice about them in terms of magnitude? It's not as obvious here. It's this business about the bottom, right? Now, here's something to notice. This was run with a friction coefficient of 0.5 everywhere, okay, between the balls and between the ball facets, okay? And so we get to this state and, nothing else is happening, right? So basically the system is locked up. Now, what if I go contact, property, friction, 0.0. So what I just did is at every contact, I set the friction to 0. Okay. What do you think is going to happen if I cycle now? It's going to probably pack tighter. Now it's going to pack to a tighter state, and there's going to be a lot of rearrangement going on. You can see, look at that, how it's rearranging. Because remember, friction gives a granular material strength. Okay. So this system is going to have is going to be more dense because I had a lower friction coefficient during the process of settling. Okay. If I ran like 7 models and I did the case with 0 friction and let it get to equilibrium, and then I did 0.1 and then I did 0.2 and 0.3, you would see that as I increase the friction, the system locks up sooner, and it locks up at a less dense state, at a higher porosity. The other thing I notice about this system is PFC is still running, that these force chains, since there's no friction, they're perpendicular, they're straight to the center, right? And that's because there's no friction, right? When I had friction, you're going to notice that the force chains are at an angle, like right there. See that? Because there's some friction holding that guy, resisting that motion, right? Okay. Now the last thing is, how do we know that we've reached static equilibrium? And so one thing that you can tell is, I'm going to cycle more. The key thing is the force chains are done, and that's what's controlling all the behavior. There might still be some slight rattling around going on, but the force chains are not changing anymore. So for our purposes of saying this is our initial packing, this should be good enough. And we could like save this and call this our initial specimen. Okay. We could also look at the, I'm going to do this. I'm going to select the ball, and there's a copy and paste. So I'm going to copy that plot item and paste it. Now I have the exact same stuff down here. Now I turn the top off, do this one, and I'm going to say draw it as an arrow. Get rid of the contact force chains, and vector quantity is velocity. How do I get this? Help me. Oh, ball arrow velocity. Vectors velocity. There we go. So let's run this thing again from the start. Notice the, oh, come on. PFC got confused. Let's run it again from the start and not change the view. Here we go. They're settling. Look at the velocities, e to the -1 meters per second, right? And what you're going to start to see, you sort of see sort of coherent motion, like as entire sections of the thing. See those 4 guys, these 5 guys, those balls are all moving in still as a unit. Now, now once it gets to full equilibrium, that was this top guy is still rotating. There's 2 balls down here. That's this guy moving down, right? Eventually, these are going to become like thermal noise. They're going to reach precision, e to the -13. There's still some coherent motion in here. This is why these sand piles take so long to come to equilibrium, okay? Because there is coherent motion. One guy starts moving, the whole thing has to rearrange. Now at this point, we ran this with the model solve command, and we used a ratio average of 1 e to the -5. And what I've already shown is that the force chains are not changing anymore, and the velocities are getting very small. And so this is 18,000 cycles, right? So this, if we run it some more, 5,000 more cycles, you can see the velocity e to the -13, okay? So using this ratio, model solve ratio average of 1 e to the -5 is in most cases sufficient to get us close to static equilibrium. And the last thing I wanted to show here is we're taking histories now, and we're monitoring the actual ratio average, that number, which is supposed to go to 1 e to the -5. So if I look at those histories that I was already monitoring, so history chart, I turn off all these other things, ratio average. And so you can see how that thing has then been going, getting lower and lower and lower. And it's still bouncing around here because those, can you see those bouncing around there? That's because there were those slight rearrangements in the system. And so we didn't have an overall unbalanced force that was really small. And then this is also, I can add, take that one off, unbalanced maximum. This now is the magnitude of the worst case unbalanced force in the system. And so again, it's bouncing around down here because there are those out of balance guys that are acting. And remember, we're taking the ratio of these average unbalanced force divided by a sort of metric of the force in the system. Okay. And you can watch this. If we actually run this and add the balls and stuff, you can see how things are rearranging as we do this and how that's being reflected in the unbalanced force. As we run this, and you can see these big unbalanced forces, right? And as this thing is trying to come to an equilibrium point, you see these big bumps. Each one of these big bumps is a big unbalanced force because one of these guys is now still moving and it's unbalanced until it gets to its equilibrium point, right? Okay. So that's kind of telling you a little bit about the history of the system. Okay. So now what we're going to do to finish things off for the last 15 minutes is we're going to work, and we're going to actually build a system like this, and then we're going to squeeze it from the top, and we're going to monitor force as the force builds up, force and displacement. It's like a crude biaxial test. So this is number 6, called Pack Box. Okay. And there's a thing in here called solved. And wait, is that what I want to do? Yeah. So I'm going to open up this thing. No, let's not do this. Let's actually do this. Well, let's take a look at this. Hold on. Here we go. This is going to make my initial packing. This is pretty much just like what we did before. Okay. Except let's just run it and look at it. My vessel. There's my initial packing, and it's getting to a e to the -5. Notice one of these guys blew out because he got pushed too much overlap, and so he's just kind of sitting here. If we were going to like make a specimen, we might give a delete command and delete everybody that's outside of the range of this to get that guy out of there, because he's not participating in our world here. So let's just look at this. It's stuff we've already done. Give a domain, linear contact model, KN, KS, and friction. Create this box. We call it material vessel for MV. Okay. Notice we're not using the generate command now. We're using the distribute command. And so what we do is we can give things from a size distribution. And we'd say for each chunk of the size distribution, where radius goes from something to something, what's the volume fraction of that portion? Okay. And then we say, what's the target porosity? So for example, whoops, return. If I run this, there's going to be big overlaps. And this is the number of balls, 502, that give me a porosity of 0.16, 502. If I go for a porosity of 0.05, instead of 502, there's 568, okay? If I go for a velocity, a porosity of 0.37, or let's do 0.5, now there's a lot less in there. They're not even going to pack. So if I run that, whoops, initial pack. If I do this, and I look at it, and I continue to cycle, they're just bouncing around. They're not actually even in, they're not packed, right? Because the porosity I said was too low to be able to pack them. So what I'm doing is I'm able to control things with this porosity. So if I do 16%, and let's do a pause. So this is what it looks like with the big overlaps. And now when I hit continue, it pushes out like crazy. And then it goes until it gets packed. Notice this packing occurred really fast. It didn't take anywhere near as many cycles because I've got this thing surrounded, and I've got some reasonable pressure. Okay. Notice also some of these guys, look at there, they're shielded. There's a compression chain around here. Look at this guy. He's not have any forces. There's no forces there. He's surrounded by a cage of compression. This was what will typically happen. The more particles I pump in here, the higher the pressure on the walls, the less of those floating particles there will be. Okay. Now let's make this porosity really, really small. So there's a giant number of particles in there. Now, what's going to potentially happen here when I first start cycling, there's giant forces here, okay? Those forces might be enough to take this particle and give it such a high velocity that it actually goes through the wall. Because remember, from this picture, here's my ball, and if this guy is moving at a certain velocity v, given the mass of this guy is going to begin to penetrate, reach some depth, and then go back. The higher this guy's velocity, the farther it's going to penetrate before it goes back. Okay? And the amount of stiffness here is going to matter. The lower the stiffness, the deeper the penetration. So because you have these high velocities with the high overlaps, it's possible that this guy is going to go, and it's going to, the deepest penetration might be here, which means suddenly the contact goes to the other side and he goes shooting out. Okay. So to reduce that chance of that effect happening, because we know that after the initial velocities get settled down and those big overlaps get removed, the system is going to be a nice, reasonably packed system. So what we do is when we cycle for the first 1,000 cycles, we say calm, which means take a total of 1,000 cycles, but every 10 cycles, set all the velocities to 0. So basically, it's got a huge force. It starts moving really fast, and then we set the velocities to 0. So then it starts moving really fast. We set the velocities to 0, which tends to calm the system. So there's less likelihood that it's going to blow out of the walls. Okay, this one has a crazy amount of overlap. So these are probably potentially going to go not too bad. It didn't actually go out of the walls. Just that one guy did. So now it's packed, and it's packed tighter. If I didn't do this calming step, or if I just did this, and I just did the 1,000 cycles, it's likely that these guys are gonna, there's a few more. There was 2 over here that went blowing out, okay? Notice the thickness of the force chains. This is much more tightly packed. Holy smokes, it's still packing. So you got these very high forces. So for example, if we said wall list attribute force, that's not it. It's supposed to be just wall list force, I think. Oh, come on. Wall list. Oh, come on. Attribute. Come on. How do I list the forces on the walls? Oh, it's called force dash contact. Force from all the contacts. So notice, let's look at the bottom force. The total force pushing against the bottom wall has a small x component, but a large y component. So it's minus 1.8 E7 approximately. And that was with a porosity, I think, of 0.03. 0.03. Now let's use a smaller porosity so there'll be less balls in there. And now when we run this thing, you can see right away that there's less compressive force in there, right? Because we have a fixed size vessel, but we have less particles that we ended up generating. There's also more guys who are floating around that are not in contact. And now if I list force of the contact on the bottom, now it's 6.5 E6. It used to be 1.8 E7, right? And obviously if I make the porosity too small, they won't pack at all, okay? So what we typically do is we choose a porosity that we know is going to give us a reasonable pack, okay? And then what we do is we specify our size distribution using this distribute command. So let's go and to illustrate that, let's do 30% of the balls being bigger. So I'm going to copy this and paste it. Alt edit copy, alt edit paste. I'm going to comment out what I started with. So now I'm doing 2 bins, and let's have the first part be radiuses of big ones, 0.15, 0.15, and let's make volume fraction is 30%. Now for bin number 2, I'm going to have it be smaller, 0.04 to 0.08. But notice I can keep that porosity at 0.16 because I know that that's going to give me a reasonable packing. Okay, so now all I'm doing now is just given a size distribution. So now if we look at it, and it didn't like this, volume fraction must fit sign to 1. So volume fraction here is supposed to be 0.7. There we go. Notice also I got these 3 dots. That means line continuation. So that means this is all one command. But this way I can break it up into multiple lines. So I put the 3 dots there. So if I look at this one now, you can see I got big ones in there. So this is going to have a highly different world, a highly different set of force chains. This is going to be a very, very different system to the one before. And my force chains, I need to rescale them even now so that I can see this better. So I go to contact force chain, shape, cylinder, target 0.01. That means the biggest one is 10% of the size of the width of the screen. So let's do 0.02. There we go. Now I've got it rescaled. But you can see how you can specify the size distribution by essentially breaking up that size distribution into different chunks by different volume fraction. And then the next thing, everything you've learned here is with PFC 2D, but the same exact stuff applies to 3D. It's the same set of commands, okay? It also applies to clumps and to rigid blocks. But so instead of saying ball distribute, you would say rigid block distribute. So let's take a look at that. And so that's in the directory called box of blocks. So I'm going to open this. Now you're going to see that this data file is almost exactly the same. What we're going to do here is we're going to create shapes. Well, let's just show it first. We're going to create squares, triangles, and circles, and different volume fractions and sizes of each. And now we've got them packing. And there's the force chains, right? All the commands are almost the same, except we have to describe the shapes. And so that's going to happen here. What we do is we create a template that is a square shape. And we create a template that's a circular shape and a template that's a triangle shape. And we could make a template that's any shape by just giving this set of facets or vertices, okay? Then what we do is we give the distribute command. So what we're gonna need to tell it, here's the region of space to create stuff in, that box from 02 to 02. We're gonna do 3 bins. The first bin is gonna have a volume fraction of 10%, and we're gonna draw from the template that are squares. We're going to orient them in some random way. This is the azimuth and the size of these things. And so what it's going to do is we're saying the sizes of the squares are a uniform distribution between 0.2 and 0.3 meters. So what that means is it's going to take that square and it's going to self-similarly scale it to be bigger or smaller so that its size lies in this region. And then the question is, how do we compute size? Because it's not a circle. It's not as the size is going to be, we're going to take the shape, we're going to compute its volume, and we're going to say, what's the diameter of an equivalent volume sphere? And so that's why we're saying diameter here. And so there we go, square. So volume fraction here of square, we're going to have 10% squares, 80% circles, 10% triangles. And we're shooting for a porosity of 0.20. Everything else is the same. Density, damping, except now instead of ball, we say R block, right? And so again, just to watch that with the force chains, I mean, it's a super powerful thing, right? Because now you have these general polyhedral shapes, but all the scheme we talked about with generating the packing and all that is all going to be the same, okay? And then the last thing to show here, and then we'll be done, is I'm going to open up that thing we just looked at. We're going to say solved. And we're going to do a biaxial test on this thing. And this biaxial test is in here. So first thing is we make the initial pack, and then we call the data file called biaxial test. So initial pack is what we've already looked at. Let's get rid of the pause. This is the initial pack, my vessel. Oh, and let's get rid of these weird sizes just to make it simpler. Let's go back to this one. So here's my vessel. There's the initial system getting packed. Okay. And now what we're going to do is run a biaxial test on it by just using the walls. So we're going to keep the side walls with the velocities of 0, just like they are, but we're going to make the top wall begin to move down. So very simple. Restore the initial pack, give it a title. So I'm actually making the top wall move down and the bottom wall move up with those two commands. And then I'm monitoring, right, the total force on the top wall and the total force on the bottom wall. And I'm also looking at the forces on the side walls, because as I squeeze it, the forces on the side wall should get bigger. Okay. To make it even more interesting, I'm putting a measurement circle in, and I'm measuring the stresses using the measurement logic. So let's just run this thing. So we're squeezing top and bottom. Can you see how the top is going, moving down, bottom pushing up? Okay. Now we had those histories. So we created another plot view called my stresses, my forces. And this is showing those 4 histories. And so what we're seeing, if we looked at this carefully, we would see that the top force is positive, the bottom force is negative. They should be equal and opposite if you're in equilibrium. And notice that the top and bottom forces are increasing because we're squeezing it. And notice the side forces are also increasing it, right? This is that K-factor business, right? You get this natural, you squeeze it vertically and you build up stresses horizontally. This is a Poisson effect of a granular system, right? So this is our crude uniaxial strain test that we just did. If we took these forces and divided by the cross-sectional area, the length and unit thickness, that we could call those stresses, right? And so here we made another plot item, and now we're monitoring histories, because remember, we were taking histories of the measurement stresses in the X, stresses in the Y. And so that's what this is, my stresses. And here we're saying the Y stress is bigger than the X stress. It's compressive. And just the one last thing, see if this is making sense. I'm going to say wall list attribute force contact. I think that's what it's called. So let's look at the top and bottom. So the Y component, it's 1.4, it's 1.4 E7 and 1.6 E7. They're almost equal and opposite. So let's use 1.5 times 10 to the 7 newtons. I'm going to divide that by the cross-sectional area. The width is 2 and the unit thickness is 1. So this becomes 0.75 times 10 to the 7 newtons per square meter. So that's 7.5 times 10 to the 6 newtons per square meter of stress. And so my measurement circle was giving me 7. There you go. It's close to 7.5 times 10 to the 7, which is just a quick crude confirmation that the measurement logic in this system, that basically the measurement logic is looking at the force chains acting here, and it's doing some interesting math on that to come up with an equivalent stress. And that equivalent stress is almost the same as the stress that we're applying on the boundary, right? And so when we actually do our triaxial tests on our real synthetic specimens, we're going to be measuring stress both by taking the external boundary, the platens divided by the area, and we're also going to be measuring stress internally to the system. You know, the one that's coming from the platens can be directly compared to what you measure in a true triaxial test in the lab, right? But in addition, we can measure what's going on in the middle. And when localizations start to occur, the stress in the middle is no longer uniform. It's not the same as the stress on the platens, and we'll be able to watch all that develop. Okay.